and I changed the splits. I think we found that the AUC did not change very much. And we talked also about what AUC means. AUC and accuracy are two different ways of evaluating a classifier. We'll talk more about flow situation. We want to use all of our data, not remove some because classes are unbalanced. So what we want to do is to train this, and so let's see. And what do we do here? Okay, so in this unbalanced case, we have a very unbalanced section. Now, when you have unbalanced data, accuracy is not the best method. Both class. And one way to do this is F1 score. So you can download that. So he talked about how we Oh, so this is an illustration of why F1 score is useful. Okay, so here's a table that shows some different F1 scores. Okay. All right. So that's the idea behind F1 score. Okay, so if we run this cell, what do we get? So let me see. I'm sorry, I forgot my mouse today, which is going to cause me problems. Okay. All right. So in here you can see that we did do two classifiers, logistic regression and random forest. And the F1 score is not that much different between the two. Okay. All right. So in this training, we selected an option called class weight equals balanced. This is something that is done in scikit-learn to counteract the effects of unbalanced classes. So it counts the minority class instances more strongly than the majority class. So you can see where that is in the code. If we go up, look at the code here. Here you can see class weight equals balanced. Just to review how this code works, what you do is you set your model as logistic regression. Here's where I set that my model that I'm going to use is logistic regression. And here is where I do perform the actual training. I fit the model. So there's two stages. You set the model and then you train it. And then you can use the model to make predictions. Okay. So set the model, train it, and then here you do, and then you predict with it. This LR represents the model logistic regression. Okay, it's a variable. This represents this model here that's trained with this random state with these iterations and the class weight balanced. Okay, so model, fitting, and prediction. Okay, and we do that for both models. Okay. All right, so if we do this experiment where we do class weight balanced and class weight not balanced, you can see the difference. Sorry, I opened the wrong one. I should be opening the one that's solved. So sorry, let me open the one that's solved. I thought I opened the correct one. So I'm going to have to run through these cells very quickly. So I'm not going to save this. I don't, is it empty? That's strange. Let me close it and open again. I'm not sure why it's doing that. Sorry. Oh, no, I don't want this. I want amplified solve. And I don't know, do you have the same problem with yours? Is it empty? Okay, I'm not sure why it's doing this. I will get another copy because this is not good, is it? Okay, this is not good. I mean, VS Code should open with it. Let me find another copy and see if I can fix it. Now you can set the threshold anywhere you want. You can say, well, if my threshold is 0.4, then I identify those below 0.4 as negative and those above 0.4 as positive. So you can see if I set my threshold at 0.4, in this case, all of the reds are to the right of 0.4. You see that? If I set here, maybe I can make this bigger. I think I can make it bigger. Let's see. Well, I can just zoom, I think. View and zoom. Zoom is here. There we go. Okay. All right. So I hope that's a little bit more visible. Okay. You can see all of the red are to the right of 0.4. So if I set my threshold at 0.4 and say all of the ones that have value less than 0.4 are blue, all the ones that have value greater than 0.4 are identified as positive. I don't make any errors by mistaking positive for negative. But I do have several negatives that I mistake as positive. So you can see the threshold here in some way is the best choice. It only mistakes this small set of negatives as positive, and it mistakes this small set of positives as negative. But you can set this threshold anywhere you want, depending on what's important. We talked previously about how sometimes a false identification is more costly, or sometimes a misdetection is more costly. So where you set the threshold really depends on your own goal, on the goals of your particular application. So if you set the threshold in different places, you will get different values of precision and recall. The farther to the left that I move this threshold, the greater the recall, but the lower the precision. The farther to the right that I measure this, the lower the recall, but the greater the precision. Okay? So there's a trade-off. Okay? And I can plot my different values of precision and recall for different different values. Now, actually, this is not precision and recall. These are related to precision recall. This one's called true positive rate, and this one's called false positive rate. This is the fraction that the fraction of the ones you identified positive that are actually positive. Okay. So in fact, this is the same as precision, and this one is false positive rate. It's not quite the same as recall. This one is the fraction of that you have identified positive that are not positive. Okay. So there's this trade-off between them. Okay. So as you increase the threshold, your true positive rate will go down, but your false positive rate will also go down. As you increase the threshold, true positive rate goes up, false positive rate goes up. This line here, this 45-degree line, indicates random guessing. It means that I'm just guessing that any instance I'm equally likely to be true or false positive. Okay. So your curve should always be above the 45-degree line. If your curve is below the 45-degree line, that means that your model is backwards. You should set criterion the other way. Okay. But any reasonable model that sets a good threshold will have a curve above the 45-degree line. And the area of the curve, what's called the AUC, is the area under this curve. Now, the maximum value of the area is 1, which is attained by this yellow curve. This yellow curve is immediately has a true positive rate of 1 for any false positive rate. So that means that I can attain true positives perfectly without any false positive. So this curve has an area of 1, AUC equals 1. This is the best possible classifier. So typically, if you have an AUC of 0.9, 0.95, this is good. It also depends very much on the application. Right. So this is showing the same thing graphically. Right. Really, this is just a representation of the same thing. Okay. So I'll allow you to read this yourself. These are several examples that illustrate how AUC works. And in this case, you can think of this as the score from 0 up to 1. And here you have the diseased and healthy. As you move to the left, you identify fewer, make false identifications of fewer of the empty cells and more precision, but less recall. All right. So you can look at these examples. So this is the next topic we'll get to. All right. So let me pass by ROC curve. So I presented ROC curve, but in some cases, especially when you have very imbalanced classes, the ROC curve is not useful. So you need to know when to apply which tool in which circumstance. Okay. For example, if you do have a case where you're trying to identify stunted children, right? You want to set some kind of threshold. For instance, you set a target for the recall. In other words, you want to set, I want to identify this percentage of children that are stunted. If I set that target, then that will allow me to set my threshold. And once I set the target, then the recall is what I specify. The precision will be determined by the model. I cannot set both the recall and the precision. The recall determines the precision. So if we set the recall at some value, okay, so let's see, I guess I've run it 3 times. Sorry. Let me run this to make sure everything is fine. But here we have a precision recall curve, which so the precision recall curve looks quite different from the ROC curve. In this case, let's see, precision here, you can see precision higher, and then as the recall goes up, the precision goes down. From this, you can see this is quite irregular. This is because the data sets are relatively small. And you can also see that there's really not a very clear difference between logistic regression and random forest in this case. The random forest is worse at higher recalls, but it's better at lower recalls. Okay. So this is a case where you would look at the specific curve to tell which case you would want to use. And in this case, the random. Wish I had my mouse. Sorry. Down here. The dotted line tells me random guessing, and the reason why this is at 0.17 is because the fraction of stunted children is 17%. So if you randomly guess whether a child is stunted or not, you will be correct 17% of the time. So that's your precision. Right. So let's go down. Whoops, sorry. We go down, and here we try different recalls. So here, in this case, the target recall was 0.7, and when the code automatically tried to find the threshold that gives you 0.7, it got 0.706, so that's very close. It can't get exactly at 0.7, and the precision was about 0.279. So in this case, 70% of the stunted children were correctly identified, but that means that only 30% of those identified as stunted were actually stunted. So for example, that means you had 86 children that you would have to investigate further. So if we do so this was just for one particular recall. Here we can do a sweep and look at multiple targets. Okay. You do that with a loop. You have these 3 different targets. Okay. So you can see how, as the target changes, the threshold changes and the precision changes. Okay. So in fact, it's quite interesting that the precision does not go down that much, which is quite interesting. That's something to look into further, that the precision does not go down that much. All right. Now, every model has what are called hyperparameters. What is a hyperparameter? Hyperparameter is something that you can change, that you can adjust in your model. For instance, logistic regression has something called regularization. When you have logistic regression, your model has several coefficients. Most models have coefficients. Now, if you have a lot of large coefficients, then this means the model is rather complex. What you want is a model with small coefficients. Sometimes you have a model with large coefficients and the two factors work against each other. That means that your model is tending to be overfitting. So we'll talk about overfitting in a moment. But there is this parameter, this hyperparameter, that allows me to tune my model. For random forest, if you think about random forest consists of decision trees. It consists of a number of decision trees. I showed a picture of decision tree, I think, on the first day, where you take your data instance and you make a decision to go one way or the other way, depending on the value of some parameter. Now, the depth of the tree is the number of decisions that you can make on any particular data instance. So if you have deep trees, you can make many decisions. Now, one parameter you can set for your random forest is the maximum depth. If the depth is larger, your model is more complex. If your depth is smaller, then your model is simpler, but it tends to underfit. Okay. Right. So maybe at this point, it's a good idea for me to talk about this concept of overfitting and underfitting. They also call this bias and variance. In this context, a bias corresponds to underfitting, variance corresponds to overfitting. So that's in the notes here. Okay. So if you look at what it says here, it says a model should learn the true pattern in the data and not random noise. Models can be wrong two ways, bias and variance. These two work against each other. The best model will balance errors from both bias and variance. We identify the best model by finding the lowest validation error, which is not necessarily the one with the lowest training error. Okay, so let's go through this a little bit more carefully to understand what this is talking about. Okay. Now, of course, you want your model to learn the true underlying pattern in the data, but there's always noise in the data. So some example you can see down here below. Here's an example of data. This would be data where you have an independent variable on the x-axis and a dependent variable on the y-axis. And this is showing you the dependence of the dependent variable on the independent variable. Now you can see very clearly that there's a curve dependence. As the dependent, maybe I can actually write this just to make this clear. So in this case, your dependent variable is here. This is your independent variable. And then this is your dependent variable. Independent variable typically is something that you can control. For instance, independent variable could be calorie intake, and dependent variable be weight of the person. Okay. Of course, someone who takes in more calories will probably weigh more. But often when you're doing a model, you're trying to find the effect of the independent variable on the dependent variable. Now you can see that there's a curved dependence. But this linear model is not capturing the curve dependence. Now, linear models have two parameters. It has the parameter which is the slope, and it has the parameter that's the intercept. Okay, so the model is simple, but it's too simple. You need another parameter that can capture the curved nature of the data. So in this case, a better fit would be a model with 3 parameters. Okay. So in this case also, this is the same data with a different fit, right? So I'm still fitting my curve here. This is my dependent variable. This is my independent variable. But you can see that my model has 3 components. So this would be a model like y equals ax plus b. This would be a model something like y equals ax squared plus bx plus c. Now, of course, this does not fit the data exactly. A model, you could make a model that's much more complex that fits the data more closely. You can see here that this model actually goes through the data points. So if I calculate the error is small. But it's quite clear that this model is catching random effects. It's not catching the underlying principle of the data. So the error is reduced, but it's too detailed. And this might be some model that has several parameters, not just 3 parameters. Okay. So this model, this underfitting model, you would call this a bias model. And you call this overfitting model, you would call this model with a high variance. You can see the variance. It wiggles a lot. It's going up and down. Okay, so that's why they call it high variance. Okay. So I hope you can see clearly the trade-off. And what you want to do is to balance these two. So there's always this balancing between overfitting and underfitting. All right. Okay. All right. So these are just some more examples. It's the same thing. Okay. You can see several balances. Yeah. Now, in the process of training, when you train a machine learning model, you often do several iterations to get a better and better model. You start with one model, and then you make improvements based on the results that you had previously. You run through the data several times. Now, as you do this, your trained model will become better and better on the training data. So this training error is the error computed on the training data. Okay, sorry, let's get this. This training error is error computed on the training data. Okay. Now, this validation error is error computed on a held out validation set. It's the error computed on a validation set. All right. Now, what's a validation set? Validation set is part of the training set. It's part of the training set, but it's held out to evaluate how the model is doing during the training process. Okay. So this evaluates, you can say this evaluates the progress of the model. Now, you don't need a validation set for all types of models. You typically you need a validation set for something like, so a validation set is used for, you need for deep learning. So mostly for deep learning. But for models like logistic regression, support vector machine, you do not need a validation set. So only some models require a validation set. Okay. All right. But the overfitting, underfitting problem is always there. Okay. Okay. So this is just saying the same thing. Okay. So underfitting has high bias, low variance. The training error is high. The validation error is also high. The good fit has medium bias, medium variance. The training error is low. The validation error also stays low. Overfitting as you continue, the validation error gets higher and higher. Okay, because you're trying to catch aspects of the data that are not actually in the underlying principle of the data. Okay. Right. So one way to counteract this problem is to use cross-validation. So you don't just use one validation set. You divide your training data into several parts, and you use parts of the training data as validation, and then you average the results that you get for these different validation sets. Okay. So here again, you can see some examples of this. Now, there's two reasons to use cross-validation. One is to tune these hyperparameters. One is to evaluate evaluate how good your model is. So there are two uses for cross-validation. If we look just at hyperparameter tuning, you can see below how this works for hyperparameter tuning. Okay. So here we have we have a code here, and what this code is doing is it's trying different random forest models with different tree depths. Okay. You can see here this array has depths 1, 2, 3, 4. Okay. So what it's going to do, it's going to do a fit with every single one of these depths. And then it's going to get a training score and a test score. Okay. So let's see how this works. Okay. So in this case, we're not doing cross-validation. We're just doing a simple test to see the effect of different parameters. Okay. So it's going to give me a training score and a test score for each one of these depths. So let me run it. And you can see what happens. Okay. The F1 score, as we mentioned, F1 score is a good way to evaluate this classifier on this particular unbalanced data. Okay. So a high F1 score means the classifier is doing well. A low F1 score means it's not doing well. Now, the training F1 is the F1 that you're getting on the data you use for training. The test F1 is when you use your model on new data. Now, you want your model to perform well on test data, okay, because that's representative of the data that you'll actually be using the model on. But you can see here that as the depth of the tree increases, my model becomes more complex. It becomes more able to fit the training data, but it does worse on the test data. So this is a clear example of overfitting. Okay. Now, on the other hand, you can see when I only have a depth of 1, you can see in this case the training data is actually worse than the testing data. Okay. That means I could have done better. Okay. So in this case, the model is too simple. I do want to increase my model. Instead of having trees of depth 1, I want trees of depth 2. It can perform slightly better. Okay. All right. But you see that actually as I increase the depth, my model's not improving. This here could just be random chance. The fact that this is a little bit higher than here, it could just be random chance. So when you're doing training, when you're comparing hyperparameters, you do want to make a comparison like this. As your parameter becomes more complex, you want to make sure that the model does not the model actually performs better on testing set. Okay, right. So let's see. So in this exercise here, it says changing a setting in the bias variance plot. It says scroll up to the cell inside the depth loop, add min samples equals 20. Okay. 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 And then so if we do it for for a different parameter. Now, this one here is a different hyperparameter. This is a different hyperparameter that is characteristic of random forest. Okay. So if we do this case, let's compare no minimum samples per leaf with minimum samples per leaf. Okay. Do you see any change? Is there really any change here? What change do you see? All right, it's good to look at data and try to see a difference in what happens when you make a change. All right, these numbers look quite the same. So are these two sets of numbers the same? What do you see that's different? Okay. Like I said, it's important to be able to look at data. If I look across here, you can see that these numbers are getting quite big and almost going up to 1. Now, if I look here, you can see the numbers are much more controlled. And for test, you can see that for test, the test is not that much different. It's still around 0.4 for all the way across. In this case, it actually got worse because of the overfitting. Here it did not get worse, but also the training accuracy did not get better. Okay. So what's going on here? This is limiting the complexity of my model. This is saying I cannot make decisions on too small a proportion of the data. Okay. So it limits the complexity. It limits the refinement of my model. So this does not allow me to make a model that's too complex. By limiting the complexity, it also limits the possibility for overfitting. Right? And let's see what we have here. Now, another concept is feature importance. Okay. Sorry, I really wish I had my mouse. I don't know if somebody has a mouse I can use. Might be mother's height. It might be mother's education level. It might be some other aspect of the data. These are called features. Now, some features will be more important than others when predicting data. Okay. So there's a way to measure the importance of different features. So if you identify the features that are important, you want your model to focus on these important features. Okay. You can actually remove the unimportant features and just look at the important features when you're making your model. So in this case, you can see that the feature importance that it found, these 3 features were more important for this type of random forest model. Okay. For this type of random forest model, if we look at this, we have so we have 100 estimators, which is 100 trees. You said class balance, and what's the max depth? I wish I could make this go away. I wish I could make it go away. Let me just see if I can do this. Okay. All right. So this allows a depth of 10. Okay. So with a depth of 10, the model is fairly complex. So in this case, you can see that the three most important features are age in months, maternal height, and wealth quintile. Now, if I change the depth of the if I change the depth of the tree, if I change the allowed complexity of the model, I may get 3 different features that are important. Okay. And what that means is that if I only allow a depth of 3, I can only make 3 decisions on each tree. Now, you can see that age in months is still important. Maternal height is not important anymore. Wealth quintile is not important anymore. Okay. So in this case, you get a different priority depending on what your tree depth is. Okay. Okay. All right. Now, we talked about data leakage and how to prevent it. Now, what's very good about scikit-learn is that it will automatically guarantee that for you. You have this pipeline feature that enables you to construct your machine learning training procedure without any data leakage. Okay? So, so this actually sets a pipeline. It tells me what model I'm using, how I'm treating the data, and it will run me all the way through the training process. Okay. So if I run this, and I do model selection, then I get results for my models. Sorry, it really is difficult without a mouse. I should have brought it today. So I think what I want to do is, all right. So you can run your pipeline and get your models, but then, as I've mentioned before, you really want error bars on your final result. You don't just want to report one number as the accuracy or F1 score for your model. So one way to do this is called bootstrap resampling. This is the best way to determine the actual accuracy of your model. So this will give you a value, and I'm sorry, I can't find it. Okay. All right, it looks like I may have forgotten to run something. Let me go back and run all just to make sure I've run everything. All right, it looks like it's getting there. Did it finish? Let's see if it finished. Okay. Okay, so it is coming out now. Sorry. All right, the fact that this is so jagged is something that really you would want to look into. Okay. Right. So so here you can see that we're actually quite far short of perfect calibration. Okay. So I think I'm going to leave this as an exercise that you can do yourself, or you can look at the answers. Here you can see you have 3 models. The ROC curves are similar, and the AUCs are also similar. So I think I'm going to stop here and take questions. And then in the next second hour, we can go through the third notebook. So I'm ready to take questions. Is anybody there? I think she's sleeping. Okay. Yes. It's time for questions. Yeah.
A round of applause for Professor Chan. So now it's time for questions, and I'll take the number ones. If you have questions, please raise your hand. Questions, clarification. 1. Yeah, that one. Is anybody raising his hand? Okay, so we'll take this first question.
Thank you, Prof, for this session, though it was quite a lot. I believe when get back, we'll take time to run through it. So while we are presenting, when you are talking about maximum debt, changing of the values, and also iterations, I couldn't really grasp it very well. I don't know if you could say a few things about both terms. Thank you, Prof.
Okay, so let's go back. Let's go back. Go back. So, so let's show. So first, let's talk about what maximum debt. No, maximum depth. This concept relates to tree-based models. Okay. Okay. All right. So a random forest consists of several decision trees. Now, maximum depth means that no tree is allowed to contain more than a certain number of decisions. So for example, if I write my decision tree like this, right? Decision trees are often represented something like this. Right. So in this case, this represents a decision. For instance, suppose I want to buy a cell phone, right? And then you make a decision. You make a decision based on price. So maybe price is greater than price, whether it's greater or less than, I don't know, 100,000. And then here you say yes, and here you say no, right? Actually, I should just say price less than 1,000. Right? Then here you make another decision, right? So in this case, it would be, say, maybe a RAM is greater than 4. And then this would be yes, no. Okay. And then this is your outcome, right? And then here you could assign a rating to it. Maybe this is rating 1, rating 2, and this would be rating 3, and this would be rating 4. Okay. So this would be another decision. It doesn't have to be the same one. This could be color. Maybe color white, yes, no. So here's an example of a decision process. In this case, the depth is 2 because you've made 2 decisions. Okay. So you can see that the more decisions you have, the more complex your model can be. Now, you also mentioned something about what was the other part that you asked about? There was a different concept you asked about. Oh, iteration. So some models. So I'm sorry if I put those two concepts together because they're not related. All right. The depth of tree depth is not related to number of iterations. What I should say is that some machine learning models are trained through an iterative process. So in particular, deep learning models are trained and retrained using the same data. And there's a terminology for that. So I think you can say, so each retraining is called an epoch, I think. I think it's called an epoch. I'll have to check that. I think that's what it's called. Okay, okay, okay. So sometimes you may train 50 or 100 epochs. You continue retraining until there is no more improvement. It's something like if you want to take an analogy with human learning, it's like taking several tests, right? So I could say a human learns a subject by taking several quizzes, okay, before the test, right? So this is an iterative process. You don't just take one quiz before the test. You take several, okay? And each time you take the quiz, hopefully you improve, okay? All right, so the question is, how do you know that you're really doing better? So I can give you an example of a usual process for doing this. So, here's an example. Suppose I train a deep learning model to recognize images. All right. So I'll take my data, I'll take my image data, and I'll take 20% for testing. I'll take an 80% for training. But then I further divide the training set and I split off a validation set. I take 70% for actual training and 30% for validation. Okay. So I can say I can perform one epoch. Okay. So during the first epoch, I run all of my data through the model to get a first approximation of the model. Right. Okay. Then I apply that model to my validation set. And I get a score. All right. Now, during the second epoch, I do the same thing. I'll get another score. And what you're going to do is you're going to repeat until you stop getting better scores on your validation set. Okay. And at that point, you say the model is trained. All right. So they have these performance curves. So typically you will see performance curves something like this. Okay. So this is going to be your epoch number. Okay. And you're going to plot two scores. You're going to plot your training score and your validation score. So my training score, I should get better and better accuracy. Often you'll see two types of graphs. You'll see a graph for accuracy and you'll see a graph for loss, for training loss. Okay, so I'll make this graph is for accuracy, but my accuracy is going to keep improving. Okay? So it may start here. Maybe this is accuracy of 1, and it will keep improving. Okay. So this here is my training accuracy. Okay. Now you also have your validation accuracy. Remember, I have my training set where I perform the actual training, and then my validation set where I check how well I'm doing. So what happens with the validation? Validation, in fact, typically will start higher than the training. Now, there's a reason for that. And it will improve, but at some point it will stop improving. Let me change my graph slightly. I want to make my point more clear. So let me change my graph a little bit. I'm going to erase this and make it and change it. I want to make this a little bit higher. Okay. Let me do another graph that makes this more clear. Okay. So I want to make it a little bit higher. I just want to illustrate the point more clearly. And I'll start my training. I'll start my training accuracy. Maybe it starts down here. And it's going to keep going up. And maybe it goes up here. Okay. So that's my training accuracy. My validation accuracy will look different. It may start a little bit higher. But at some point, the validation accuracy goes here. Okay. So what's going on here? The fact is that I'm running my data in the training. I'm running it through the same training data. It's finding particular characteristics of that training data and fitting to the training data. That's overfitting. So this gap is your overfitting gap. Okay. This here represents overfitting. Okay. So when you have these training curves, you really want to stop your training here. You want to stop your training when the validation stops increasing. Okay. Okay. All right, so this curve is an accuracy curve. You will also see when you have these training curves, you'll also see loss curve. And loss curve just goes the other way. Loss curve will go down. Okay. Loss curve goes down, right? So there's a measure of how well you're doing, and there's a measure of how inaccurate you are. That's called the loss. So in that case, you get something like this, right? Your training loss may go down. So this is training loss. Here's your epoch, and here's your loss function. And then your validation loss is quite similar. Validation loss may start a little bit lower, but then it will stop improving. Okay. Okay. So you stop training when your validation loss stops improving. When the validation stops improving. Now, in fact, the validation may start going up again. And that's because of overfitting. It may be the validation goes here and then it starts going back up. And that's because your testing model is looking at the particular test data, is doing well on the, I'm sorry, your training model is doing well on the training data, but it's picking up these features that are not really in the underlying data. Okay. So I'm sorry, thank you for the question. I'm sorry if I confused depth of tree and iterative in iteration. Those are two completely different things. The depth of tree only has to do with tree-based models, and iteration has to do especially with models like deep learning or any kind of model where you have to do training. Completely different concepts.
All right. Thank you so much, Prof. We have three questions from the online participants. So you will read it out.
Okay. Yeah, if you can bring it here, or maybe I can find it. Is it here on the here on the chat? Is it here on the chat? Can I see it on the chat? Okay, okay. Please, how should hyperparameter tuning be designed for longitudinal health data to avoid data leakage and overfitting while ensuring that the selected model generalizes well to an external population? All right, so let me copy this question and see if I can analyze this. Okay, well, all right, well, let me answer this now and I'll do the other ones also. All right, so you can see that we have two things here that are important. We have the hyperparameter tuning, and then we have data leakage, and we have overfitting. All right, now data leakage. So as we mentioned, hyperparameter tuning. Every model will have some parameters that you can adjust. Okay, now what about data leakage? Data leakage happens when you're reusing training data for testing. Right. Now, one problem with longitudinal data, Okay, now you health people can help me. Longitudinal data means time series, I think. Okay, so this means you're taking data over time, right? Now, the the problem with this, so I wonder if someone can give me an example of longitudinal data. Are you looking at some cohort? Let's say again. Okay, malaria cases. Okay. All right. Now, I think the way that you'd avoid data leakage is you always want to, you can say quarantine your data, right? You want to make sure that you're not reusing training data for testing. Okay. So in this case, you would separate different. Right? You'd say you take some individuals from beginning to the end, right? So you have some individuals for training, some individuals for testing. Right. Now, this is very clear isolation because the individuals for test training will say nothing about the individuals for testing. Okay. So so this guarantees isolation of training from testing data. Right. Now, overfitting. Okay, so the question of overfitting, this is what I mentioned, is that you have maybe too many hyperparameters. You might have too many hyperparameters, or so what can I say about overfitting? Well, how can I say? But there are several ways to deal with overfitting. Okay, one is the way I mentioned. Okay, now often to deal with overfitting, you'll use some kind of validation data. Okay, so typically overfitting can be dealt with using a validation set. And what is a validation set? As I said, it's a preliminary evaluation of your model. Okay. Right. So validation set, but your validation data is part of your training data. All right, so I think that's the best answer I can give. There are other techniques as well. All right, but the general principle is you avoid data leakage by isolating your data, and you avoid overfitting by using some kind of validation set. Okay, so let's see what else we have here. You said there's some more also before this? Okay. Where? Okay, for the ROC-AUC curve, both the regression and RF models were below the threshold of 0.5. I don't think that's true. I'm not sure what that means. If you go back to the curves, I think you'll find that both of them were above. I'm not sure what that means because I don't think that's accurate. Maybe the person who asked that question can ask it again. I can say in general that if your model does not perform up to your expectations, you can try a different model, but it may just be that your data cannot be fit better. Real data is noisy. There are limits to how accurate you can make models. Okay. 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 All right. So here it says, how do we know when further hyperparameter tuning is no longer improving the model? Number two, If we don't use a validation set for models like SVM or logistic regression, apart from deep learning, how do we handle class imbalance effectively than in those other models? Okay, so let's see, how can I answer this question? I think I think the first question, how can you know when further hyperparameter tuning is no longer improving the model? Well, I think you can tell just because tuning, the model doesn't get better. I mean, suppose you keep adjusting parameters and the model doesn't get better, then the hyperparameter tuning isn't helping you. And if we don't use validation set for SVM or logistic regression, how do we handle class imbalance effectively? Now, validation, I don't think that validation has much to do with handling class imbalance. I think that there's a confusion there between two concepts. Class imbalance can be handled by weighting data differently. Validation has a different purpose, not for addressing class imbalance. So I think that's something different there. Okay, okay, okay. It says, please throw more light on F1 score and R squared. Okay. Now, I think those are all very different things. F1 score, I don't think F1 score has anything to do with R squared. I didn't talk about R squared. R squared has to do in particular with regression, but F1 score is something much more general. It doesn't just have to do with regression. So I think those two concepts are not very closely related. I think Charlotte gave another thing. I'm not sure what you're referring to when you say overfitting, please. Can you be more clear about that? I'm not sure what you mean. I don't know if someone else here has questions or not.
Okay, since we have two more questions, sorry, is there any other person that wants to ask question? This is the last round for questions. This will be the last round. So if you have questions now, please raise your hand. Going, it's gone. 1, 2.
Prof, I just want to give you some more clarification on bias and trade-off, bias variance trade-off,
Okay.
in relevance with the underfitting and overfitting.
Okay.
Because you have mentioned somewhere that high bias means underfitting, kind of. Yeah. So with the help of example, I mean, if time permits, then it's okay. Otherwise, maybe in this problem 3, you can make us more clear about that with some kind of diagram and all.
Well, I think that the best diagram is this one here. I actually don't like this terminology of bias because in statistics, bias means something different. When they're talking about bias in machine learning, it's really something different from statistical bias. I think you're familiar with bias in estimator, right? So let's see if I could get back where I am. Here. Sorry. I don't know what happened to my notebook. Let me go back to the PDF then and just go there. I can't find the notebook. I'll just download this. Is it coming? Okay. I'm not sure if it's coming or not. Let me see if I can find it. Okay, here we go. Looks like it is coming. I think the clearest picture is here. Now you can see that the data here is systematically below the model. So that's why they call it bias. Because if I'm looking for, if I'm trying to predict values in this area, I will be systematically higher. So that's why they call it bias. Okay, it's something that you can see that if you're in a certain, if you're trying to predict in a certain regime, you can tell which direction you're going to be off. Okay, now they call this one variance is because if I'm in a particular place, the model itself has variance. Even you make a small change in the parameter, the model prediction changes a great deal. See, like here, right here, I change my dependent variable slightly, and the prediction changes a great deal. So that's why they call it variance. But again, it's not the same thing as bias and variance in statistics, because this is not a statistical estimate. Okay, but that's the idea. That's why I prefer overfitting and underfitting. I think that's a lot more clear. Okay, but that's the idea.
All right. Prof, my question is, at what point do we draw the line on a data set that we can't really get much insights using machine learning? Because, for example, this DHS data set that we have, we try multiple approaches. Like we try to improve the F1 score, and we also use cross validation. And like generally, there isn't much difference between if you look at the results that we got. So is it a result of the actual synthetic data set? Or if we have a limiting data set, is it possible to use other approaches that can give a realistic prediction and we can actually use for, real life scenarios?
Well, so the question is, can you do better? I think there is no there's no definitive answer to that. I think some of that has to do with experience. One thing you need to be careful about, very careful about, if you try hundreds of models, you probably will get one that's good just by chance, because you're trying hundreds of models. So I think maybe I think what people typically do is before they start the investigation, they say, I'm going to try this many models and tune my hyperparameters to optimize these models. And then they just take whatever best result they get from that. So I think that's the typical procedure. Another thing is that you can get some insight just by the nature of the data. For instance, just a simple example. If you want to predict a person's height based on their weight, right? Or the other way around, we want to predict a person's weight based on their height. You know from experience that there are many, many random factors that influence weight besides height. There's the person's build, there's other factors as well. So trying to get 99% accuracy is certainly not going to be fruitful. Okay. So I can't give a definitive answer, but those are some kind of general guideline that people do. All right, thanks for the question. Are we good? Okay.
So a round of applause for Prof. That takes us to the end of this section. And now we'll go for a short break that would last for just 30 minutes. So please stretch around get something within the next 30 minutes, and let's all gather back for the